Hello and welcome back to the Alphabet of Astronomy. Today is brought to you by the letter H, and H is for hypernova. So you may have heard of nova in the context of astronomy before. There's actually several different kinds of novae. So there's just a nova, there's a kilonova, there's a supernova, and these are all based off of the word nova, which is Latin for new. And this is because they appear in the sky like new stars because they are a sudden increase in brightness. However, sometimes these other prefixes just aren't enough, and a supernova is just not enough of a description, and then you get a hypernova. Hypernovae are also called superluminous supernovae, if you want to double up on the supers, and they're also sometimes called collapsars, which is basically a portmanteau of collapsed star. So between all of this, you might get an idea of what we're talking about, which is basically incredibly bright types of supernovae that are caused by collapsing stars. Now, the term hypernovae has been used for other phenomena in the past. That wasn't kind of a set definition, but this is now the kind of present day generally accepted use of the term hypernova. And while other supernovae are caused by core collapse, for example, type 1c supernova, when we're talking about a hypernova, it's 10 to 100 times more luminous. So orders of magnitude brighter than a typical supernova, hence the name hypernova. Astronomers and our names. So the first hypernova that was actually observed was in 1998, and it was SN 1998BW, which is basically just a bunch of letters and numbers that are used to refer to supernovae as we observe them throughout the year. But in this case, it was 100 times brighter than a typical 1b supernova, and it had an associated gamma ray burst. Now, gamma ray bursts are these, as you might guess by the name, these bursts of very intense gamma ray radiation. And this observation of the hypernova with the gamma ray burst kind of helped explain the theoretical underpinnings that scientists had been trying to model of what is happening during a hypernova, and they did predict these kind of gamma ray bursts. So seeing them together was kind of confirmation of a little bit of what was happening in this event. So what is happening during a hypernova? Well, if you've watched some of my previous videos about stars, you know that the core of a star needs some sort of support to hold it up against gravity, because gravity is always trying to pull things in together tighter, and there needs to be something pushing back to prevent it from collapsing into a black hole. In a typical burning star, that thing is going to be thermal pressure from the fusion in the core. If that fusion pressure is gone, it might be electron degeneracy pressure, such as in the core of a red giant or in a white dwarf. And if that isn't enough, it might be neutron degeneracy pressure like we see in a neutron star. But neutron degeneracy pressure is basically the highest pressure that you can get. It's the biggest pushback you have against gravity. So if neutron degeneracy pressure fails, and if it's not enough, then you're going to get a black hole. Gravity is going to win. So if you have a neutron star that is being held up against gravity by neutron degeneracy pressure, and then you make it more massive, it will kind of cross this limit at which it cannot sustain itself anymore, and it will cause a collapse. And this limit is, for a non-rotating neutron star, about 2.2 solar masses. However, we're just talking about the core of the star here. So in order to get a core that massive, you need to start with a very massive initial star, especially because more massive stars tend to lose a lot of mass throughout their life. So we're talking about stars that are on the very high end of the mass range, like 30 times the mass of the sun or more. So now you have this core that can no longer support itself, and so it collapses into a black hole. And a lot of that stuff that was around the core is now going to be falling into a black hole. Now, when matter falls into a black hole, it tends to form what we call an accretion disk. Thanks to angular momentum, basically, so it can't just spherically fall inward. So it forms this disk that starts to accrete onto the black hole. And then because of that disk and the accretion onto the black hole and the magnetic fields, basically a lot of things involved, you get jets. So a lot of energy is released from the mass that's falling onto the black hole, and that energy is primarily released via these jets. And they go in both directions, kind of away from the poles of the disk, the rotating disk. So if you think about it, you have a black hole, you have a disk, and then kind of on the axes of the disk, you have these two jets that are pumping out extreme amounts of energy. Now, this might sound vaguely familiar to you if you've been watching this whole video series, and you might think, isn't this what you described in an AGN? Yes, absolutely. But we're talking about a much smaller scale here. So in AGN, we were talking about supermassive black holes, right? Millions and billions of solar masses at the center of a galaxy. But now we're talking about a stellar mass black hole. It's only, 2 solar masses or so, or maybe a little more. But it's the same concept, it's just on a smaller scale. And now even the energy being released by this black hole from the accreting matter isn't really enough to explain this intense amount of energy that we see during a hypernova. And it's not enough to explain the gamma ray bursts, because the gamma ray bursts have to have a certain amount of energy to kind of break through the material around the dying star, and you need a way to basically get that up to higher energies to account for what we see. Well, that's where this really cool effect comes in. So because these jets are being accelerated so much and the particles in them are going so fast, they're actually approaching relativistic speeds. So that is kind of speeds where you have to start to take into account special relativity. That is the fact that the speed of light is constant in basically every frame of reference. And what happens is this leads to a thing called relativistic beaming, or the Lighthouse Effect. Now this is kind of due to an interesting thing that happens when you try and deal with relative velocities at relativistic speeds, using kind of 2 different terms of relativity here, just to be confusing. But so normally, say at non-relativistic speeds, if you were in a car that was driving 50 miles an hour and you had a ball and you threw that ball in front of you at 50 miles an hour, someone that was at rest relative to the car would see that ball moving at 100 miles per hour, right? You would just add together the velocities. But now let's say that that thing was a beam of light that you flicked on, or a laser or something, and you were moving at 0.5 c, and you turn on the laser, and relative to you is moving at the speed of light, c. But you can't just say, okay, for someone that's at rest relative to you, then they're going to see that light moving at 1 times the speed of light plus 0.5 times the speed of light, which is your speed. Because they can't see light traveling at 1.5 times the speed of light. They can only see light traveling up to c. So basically, you have to take into account something called a Lorentz Factor, which basically will reduce the amount of relative velocity because you divide by the Lorentz Factor. And again, this only matters when you have relativistic speeds involved, otherwise the change is just negligible. But in these jets, they are reaching these kinds of speeds where it matters. And because of this, if you have a particle that's, a source of some sort that's emitting isotropically, that is, it is emitting in every direction, which is kind of an oversimplification to begin with, but we'll just use that as our reference to explain this. If it's emitting in every direction from its own perspective, right? For us, if it's moving at relativistic speeds, we don't see it emitting in every direction equally. It actually looks like it's emitting much more towards us and much less away from us. And that makes the light that's moving towards us appear much, much brighter. And this is how you get that really great increase in luminosity that makes something a hypernova. And this is how the gamma ray bursts become so energetic that they burst through the material and we can observe them. This is just one of the weird outcomes of relativity. Relativity is weird. I don't know if you've ever tried to work in relativity, but it is not intuitive to us because we do not generally encounter relativistic things in our day-to-day life. It's not like throwing a football or something. It is very different. But we have been able to work out how it should work, and that can help explain things like astronomical phenomena, and we need to take this into account to explain these things. So another theoretical mechanism for creating a hypernova is basically the same concept, but you start with a binary star, where one is a neutron star, and then the other star is just a, typical star going through its life, and as it reaches the end stages of its life and starts to put off all of its mass, that mass then goes onto the neutron star, and that causes the neutron star to, again, trip over this kind of set point where it can no longer hold itself up, and you get the same sort of thing happening, where it now is going to collapse into a black hole. You're going to get an accretion disk and jets. Bing, bada bing, bada boom. And if that sounds familiar to you, it might sound like the process that happens for a type 1a supernova, and that is a very similar idea, but in that case it's a white dwarf, which is a similar idea to a neutron star, except it's electron degeneracy pressure. Whereas here we're talking about neutron degeneracy pressure. So it's kind of, again, it's the same concept, but it's scaled up in this case a little bit, and that's why you get a hypernova rather than a supernova, because there's more mass involved, and mass is energy, right? So the more mass that you're destroying in this process, the more energy there is to be released. So, I mean, that's the short and dirty on hypernovae. They're pretty cool objects and a pretty cool name in my opinion. So I hope you learned a little bit of something new. I hope you enjoyed, and I hope you'll come back for the letter I. I'll see you next time. Have a good one. Bye.